All right, here we go with our final lesson of our introduction to calculus. This is where we finally get to introduce the idea of a derivative. So, real quick recap on where this is coming from. In our last lesson, we were taking a look at the idea of an instant rate of change. And so we were saying normally when we are looking for a gradient or a slope, it always deals with the idea of an average rate of change because you need 2 points in order to use the slope formula, right? We're always doing y, our second y minus our first y, and our second x minus our first x. And so we needed 2 different sets of points in order to use our slope formula. So that always gets us an average rate of change. And so we went through this whole idea of the limiting process in order to get an instant rate of change at a single point instead of the average rate of change at 2 points. And so what we did was we said if I want the instant rate of change at just the point where x equals 2, in order to use this limiting process, we're going to start with 2 points. So we went from 2 to 3, and we found the slope, and then we went from 2 to 2.5, and we found the slope, from 2 to 2.1, and we found the slope, and we kept getting closer and closer and closer to our target point of where x equals 2, just so we could zoom in on what that instant rate of change is at that point. So keep in mind as we develop this expression, h was the distance between the 2 points. And so if I went from 2 to 3, that would make h 1 because I was going from 2 to 2 plus 1. If I went from 2 to 2.5, that would make h 0.5, right? H was the distance between the 2 points, and the idea was I wanted to make h smaller and smaller and smaller because I wanted to zoom in on just our target point of our value of 2. And so essentially we wanted our h, the distance between the 2 points, to be 0 because we want an instant rate of change at a single point. And so as we went through this process of using 2 and 2 plus h and getting an expression like this one here, we can see that as h approaches 0, right, as h becomes smaller and smaller and smaller and approaches 0, we can see the limit that we are approaching. We could see that we are approaching a value of 12. And so as h became 0, right, we could see that really all we are left with is 12. And so that's how we can identify that the instant rate of change, or the slope, or the gradient at where x is 2 is simply 12, because that's where h was 0, and that's all we were left with. And so we're using that idea to get a derivative in today's lesson. The one issue we run into with the limiting process is it only works for one value. If I want to know where the instant rate of change is where x equals 2, then I have to develop an expression for 2 and 2 plus h. But what if I want the instant rate of change where x equals 4? Well, then I would have to start all over and do a new expression for 4 and 4 plus h. Or if I want the instant rate of change at -1, then I have to do -1 and -1 plus h. And I keep having to start this process all over if I want the instant rate of change at a new x value. And so what we're going to see today in this derivative process is we're going to develop an expression that will work for any x value so that I don't have to start over. If I want the instant rate of change where x is 3, I can just plug this into my derivative. And if I want it again where x equals 2, I can plug this into my derivative instead of having to start a whole new process. So for this guy today, instead of using a specific number and then that specific number plus h, we're just going to keep it general, and we're going to keep it as just x. And so that way when I'm done with all this, I can plug in any value for x into my result instead of having to start over with a new process. So real quick on the notation that you're seeing, the little f prime of x, that means derivative, and that's just, again, what we've been doing, which is just getting an expression for slope or gradient. Remember, as we go through this, slope is always y minus y over x minus x. And so that's where we're seeing in this setup right here. It still all comes back to gradient or slope. We are, just like in the last lesson, taking the limit as h approaches 0. And so you'll see how that works out here towards the end of all this. So again, when I have in a function like this, 3x squared plus 4, so we're going to start all of these the same way now. This is called the first principles method. And again, it's just like doing what we did in the last lesson, only we're keeping x as x instead of as a real number to this point. So finding the derivative of this using our first principles method. Again, I'm using x, and I'm going to use x plus h as my two x coordinates. And remember, h is simply represents the distance between 2 points. But again, the idea is I want that distance to be nothing so that I can get an instant rate of change at a single point. As always, in order to get a y-coordinate, I am plugging in my x-coordinate into the function. Well, if I plug x into this function, it's still going to be 3x squared plus 4. And if I plug x plus h into that function, so 3x plus h squared plus 4. So let's do a little cleanup on that one. If I FOIL my parentheses here, we're going to get x squared plus 2xh plus h squared. Bring down my plus 4. I'm going to distribute my 3. And we get this expression right here. And it looks like nothing else will simplify in there. So that is going to be my other y-coordinate. That's this guy. And so just like this setup describes for us, I'm just doing slope. I'm just doing my second y minus my first y over my second x minus my first x. One thing you'll see in this notation, though, is if I do this minus this, you'll notice that x minus x will cancel. So on bottom, all I'm ever going to get down there is h. So we kind of take a shortcut on that, and we just put h every time because that's the way it's always going to work out. Anytime I do this minus this in my denominator, my x's would always cancel, and I just get the h. On top, I'm doing my second y minus my first y. So here's my second y. So I'm just bringing that one up. So that's my second y minus my first y over, again, I'm doing x minus x, which is just going to leave me with an h down there. So here's our scenario. Let's just do a little cleanup on this. You can see the 3x squareds will cancel. You can see that the 4's will cancel. And so all I'm going to be left with on this, and I'm going to keep the notation going here for my derivative, is my 6xh plus 3h squared all over h. As I divide the h out of everything, I'm going to just get 6x plus 3h. So here's the expression that we're getting down to. So here's one thing I want you to understand, super important, and this is what we covered in our last lesson as well. All this has to do is the limit that we're finding as h approaches 0. So if h is becoming 0, all I'm going to be left with is my 6x right there. And so we're going to finish off this notation, say my derivative, which is f prime of x, is the limit as h approaches 0 became 6x. And so here we go. We have our derivative, and that was using the first principles method. But here's how it works. If I now want the instant rate of change or the gradient at any single point on my function, I can just plug in a value for x to get it. So if I want the instant rate of change where x equals 3, well then I can just plug in the 3 right there and get 18 as my gradient or my slope. Instead of having to start all over, if I want a new instant rate of change where x equals 2, well now I just plug in that value. So if I plugged in a 2 for x, I can see that the instant rate of change where x equals 2 is 12. So my slope would be 12 at this point right here. Or at this point right here, my slope would be 18. So we now just plug those into our derivative to get our slope. I'm going to do one more here. So you can see this one more time. Again, I have 2 plus t squared is the function. And just to go through this one a little quicker, we can see that I'm looking for the velocity at the point where t is 1, so at 1 second. So again, one of the things this gets used for if you go a little further into a little bit higher physics, or as you get further into calculus, you find that distance, which is what we're talking about right here, so this is a position function or a distance function, you find that velocity is the rate of change or the gradient of distance. And so when we find a derivative function of this guy, it becomes our velocity function. If you go even farther on that, if you found the derivative of velocity, you get acceleration. And so all these guys connect together, and that's what big thing that derivatives get used for, especially within physics, is for distance, velocity, and acceleration. But we're going to not quite go that deep here. So I just want the derivative or the gradient where t equals 1. And so I'm going to start it just like with the last one. I'll use t and t plus h instead of x and x plus h. You could use really either, but just to keep it relevant to this problem, we'll use t and t plus h. So those are my x's. And if I plug t in for t, obviously I'm going to get 2 plus t squared. And if I plugged in t plus h in there for t, so if I did 2 plus and then t plus h squared, so if I do a little cleanup on that, I should get t squared plus 2 t h plus h squared. And so there's my second y coordinate. That's this guy. Just not going to write all that again. So again, I'm just going to do y minus y over x minus x. And so if I did 2 plus, or sorry, let me start with this one. So my second y minus my first y and like I told you on the last one, if I did x minus x on bottom, you can see that the t's would cancel. I'm just going to be left with the h, so I can kind of skip to that part. Up top, you're going to see things cancel as they should. My 2's cancel, my t squareds cancel, and all I am left with is the 2th plus h squared all over h. And then divide out the h's, and you can see that I just get 2t plus h as my final expression. So remember, the idea of all this is what we just found is a derivative, which is a function for gradient or slope at an instant point. And so we're always doing a derivative as the limit where h approaches 0. So if h is becoming 0, what would I be left with? Just 2t. And so at the end of all this, my derivative is simply 2t. But remember, what that allows me to do now is to find an instant rate of change at any point on the curve that I want to plug in for t. And so if I want it at where 1 second occurs, which is the same thing as saying t equals 1, I simply plug in a 1 for t, and I can get my derivative or my gradient or my slope or my instant rate of change would simply be 2, where t equals 1. And so we're using our derivative function as a way of getting the slope or the gradient at any point on this curve. that we would like to use it for. And so this is, again, called our first principles method. It all comes back to doing slope, which is y minus y over x minus x. So hopefully that's working for us, and then we're going to see as we get into chapter 24 in the next lesson, really an easier way of getting a gradient function or a derivative using something called the power rule. So this is all that process just sort of leading up to that idea so that you get an understanding of what this function means, what a derivative is, where it comes from, and how we can put it to use as we get into chapter 24 next. So